Hey, AP Chem. So we are going to be getting into one of the things you really need to be good about acids and bases. And honestly, I feel like I say this every time, but really neutralizing acids and bases and understanding the chemistry behind them is going to be really important for a bunch of different things. One, figuring out titration, figuring out how much of something needs to react with something else, graphing a titration, which we'll be getting into, dealing with buffers, dealing with pH at equivalence point, all these different things. You need to be first and foremost able to identify the chemistry that's going on when we neutralize an acid or a base. And so that's what we're going to talk about in this video and get a little bit of practice on, and then we'll kind of build off of that in our next sequence of videos. So the first question always is, what the heck is a neutralization? What happens is a neutralization happens when acids and bases react together, effectively canceling each other out. And we've talked so much about the equilibrium, the balance between H pluses and OH minuses and all that stuff, that it should hopefully kind of ring a bell that, oh, if I mix those two things together, they're going to cancel each other out and they're going to make something. And you should probably be able to guess at this point, H plus, OH minus gives me water. And so what happens is if I, let's say, spill a bunch of acid on the counter, I'm going to sprinkle baking soda, which is a base, on the counter to clean that up. And if I spill base, I usually neutralize that with vinegar, which is acetic acid. So they cancel each other out. They're inherently balanced just by existing. And so when they react together, acids and bases always follow the same general pattern. What happens is if you mix an acid and a base together, they make two things. One is water and one is a salt. And the salt that they make is going to be unique to the acid and the base coming together. But the salt is always made from the cation from the base and the anion from the acid. And they come together, they follow oxidation number rules, and they will help you figure out coefficients for the balanced equation, because sometimes you've got a polyprotic acid or a couple hydroxides to deal with. And we'll kind of get into that as we go along. Okay, so we're going to get right into some examples, and then I'll do some practice with you at the end of the video as well. All right, so the first thing is if we mix a strong acid and a strong base together. So the example that I want to do is I want to talk about hydroiodic acid and sodium hydroxide. So if I mix together NaOH and HI, they have one acidic hydrogen and one hydroxide that are going to cancel each other out. And the H from the HI and the OH from the NaOH are going to come together and they're going to make a water. The salt that they're going to produce in this case is sodium iodide, and it comes together in a 1-to-1 ratio because sodium's oxidation number is a +1 and iodine's oxidation number is a -1, and so they cancel each other out. So that is the neutralization. They make water and the salt. Hopefully fairly straightforward. Like I said, we're going to go through some practice where I go into a little bit more detail, but this is the general gist of that. Now, if you remember from way back when, the complete ionic equation is taking a look at everything that's in that equation, and if it's aqueous, we break it apart into ions and we cancel things that are identical on opposite sides of the equation. So if I look here at my complete ionic equation, what we're looking for are common things on both sides. They are, if you remember the name, a spectator ion. Those spectator ions don't change in the process, and so they get left out of the overall net ionic, which we'll get to in a minute. In this case, we have I- on both sides. We also have Na+ on both sides, and it should be really familiar to you that Na+, basically the majority of your alkali metal ions, they're going to be spectator ions. So if we cancel those things out, our net ionic equation is actually super basic. So this is only, not super basic as in like the pH, but super easy. So what you should see anytime you mix together strong acid, strong base, your net ionic equation is going to be H+ and OH-, and that's it. Easy peasy. Okay. All right. Going to a weak acid and a strong base, we're going to mix together HF and calcium hydroxide. Now, calcium hydroxide is a strong base, but it has two hydroxides. So if we think about our oxidation numbers. HF has a +1, or H has a +1, F has a -1 for its oxidation number, calcium is a +2, and OH is a -1. And essentially, these are kind of like double replacement reactions. So the H and the OH get together, and they're going to make 2 waters this time because we have 2 hydroxides that we need to neutralize. It's also going to take twice as many moles of HF to make that happen because H is only 1 time showing up in HF versus the 2 OHs and calcium hydroxide. So this is actually a 2-to-1 mole ratio. It makes 2 waters, and then our salt in this case is going to be CaF2. Okay, now when we talk about our complete ionic equation, you would say to yourself, okay, I can do this. I can split all these things up into ions and then do the canceling. But here's one thing that you need to be aware of when we write them for weak acids, and you'll see in just a second, weak bases. Weak acids don't get split up. And the reason why they don't get split up, even though they're aqueous, is because of their actual physical nature in the beaker. And we've talked about this a bunch before. A strong acid ionizes 100%, so it's easy for those ions to kind of sit there and not do anything. But a weak acid, they stay together. They stay stuck together as whole acid molecules. And what happens is as they get neutralized, the few H pluses that are kind of floating around in solution will get neutralized by the hydroxides. And then when those get taken out, a la Le Chatelier's principle, more will ionize and they'll get pulled out. So it's kind of like a 1-2 sequence that happens. And because of that, we can't write HF as an H plus and an F minus, because if we would take a magical snapshot of it, it'd be mostly HF molecules whole. So when we talk about writing a net ionic equation, if it's a weak acid, we gotta leave it stuck together. So it's 2HF plus the calcium plus 2 ion, 2 hydroxides, mix 2 waters, calcium plus 2 and 2 F minuses. So you can kind of see here, I don't have as much that I can cancel out. And so my net ionic equation for this neutralization is going to be HF plus OH minus, and that turns into H2O and F minus. Now you might say to yourself, Adi Meyer, where did the 2's go? If you look at the mole ratios, it's 2's across the board, so all I did was reduced it. Okay? And then strong acid and weak base. And I hope you understand at this point that weak bases are like the complicated ones of everything. So every time a weak base is involved, it's a little weird, it's a little more work, and you'll see that again. If we mix together a strong acid and a weak base, here is the molecular equation. It's pretty straightforward. It's NH3, in this case ammonia, plus HCl, and it turns into NH4Cl. But you say to yourself, you told me that I need to make water and I need to make a salt. And there is one thing that's distinctly missing here, and it's the water, right? You're like, where is that? Well, here is where weak bases continue to cause us a little bit of extra drama. So when we take a look at a weak base, you should be able to recognize that when I put a weak base into water, like ammonia, it's mostly going to be whole ammonia molecules, but some of them react with water and they're going to turn into the ammonium ion and some hydroxide that's in there. So that beaker that's sitting in there doesn't have just whole ammonia in there. It has hydroxide in there as well. So there is some OH floating around in there. It's just not appearing. We just don't recognize it because it's not smacking us in the face with that OH in the formula. What ends up happening then is our hydrochloric acid, when we put it in there, reacts with the OH, gets together, makes a water, and then the chloride ion. So there's kind of this two-pronged process that happens here. We end up making the ammonium ion when the OH minus forms from the water, and then we make the chloride ion when the neutralization happens. So technically, yes, there is water being formed. It just doesn't look like it in the molecular equation, but it's there. Trust me. Now, are they going to ask you to write that down? No. Fortunately, the net ionic equation for this is really simple. It's just H plus NH3 turns into NH4 plus. That chloride ion, Cl minus, is a spectator very often unless it's trapped in a precipitate, which it's not here. So those are kind of the things that you're going to be seeing with a neutralization. We're going to go through 3 different practices, and I want you to try to figure out those neutralizations. So the first one's going to be HNO3 and KOH. Then C5H5N plus HBr. And then lastly is this whopper here, CH3, CH2, COOH, and NaOH. So here's what you should do. You're going to write these down. You should practice those equations, and then in like whatever time it takes you, we will go through those answers and see what the heck is going on. Okay? So again, pause the video. I know that you're like, no, never. No, pause the video, do the practice, and then we'll come back and see how it went. Okay? So I want you to write the neutralization reaction and the net ionics. All right. Hopefully you paused. You weren't lying. We'll see how it goes. Okay, so practice here, number 1 is HNO3 and KOH. So what I like to do with all of these is I like to take a look really quickly and identify if they are strong and weak, because it's going to make my net ionics a little bit easier for me when I go through and think about it. There's a lot to keep track of here, so if we can give ourselves a little slack, I think it's always helpful. So if we think of HNO3, HNO3 is definitely one of our strong acids. You got to know them, and so is KOH. So we've got a strong acid and a strong base coming together. Next thing I want to do is I want to figure out my oxidation numbers to make sure that everything is going together the way I expect it to. So H is going to be a +1. The nitrate is a -1, those beautiful polyatomics. K is a +1, and OH is a -1. So this is going to be a 1-to-1 ratio. Remember, it's a double replacement, so we're going to swap our cations here. So I'm going to make water. And sometimes people look at this and they're like, water just doesn't make sense. But if you think about it, water is technically an H and an OH together, H and OH. So that's where that's coming from. So it makes H2O. And if you, for whatever reason, want to write it as HOH, more power to you. Okay. And then our salt is going to be a K and an NO3 together. And just for practice, wouldn't hurt to check. We have a +1 and a -1 for our oxidation numbers. So those are good to go. So our overall balanced equation is this. Now you might notice that this is a one-way arrow instead of a two-way equilibrium arrow, and that's correct. So neutralization reactions are a one-way street. Once you turn it into water and the salt, it's not really going backwards from that process. So this is a little bit different. Now, in this case, our net ionic equation for this leaves out the spectators. So spectators in the strong ones are basically everything except for the H plus and the OH minus. So it's going to be H plus OH minus turns into H2O, and that's it. Okay. Very commonly, like I said, alkali metals, nitrates, all going to be aqueous. So they're pretty much spectator ions the vast majority of the time. All right. Hopefully that went well for you. Number 2 here is the C5H5N plus HBr. And when we look at what is going to happen here, technically, they combine together. If we look at this, this is going to be a weak base, and HBr is one of our strong acids. You should know your strong acids and strong bases, so then you should identify that if we've got a strong acid together, this must be a weak base because it's definitely not anything we've, really talked about before. So when we talk about this coming together, all they really need you to do for the molecular equation is combine these two. Because it's a weak base and a strong acid, you don't have the kind of complicated exchange that's happening. You just smush them together. Now this one's a little weird because of the formula, but I'm just going to put C5H5NH because that would have been our conjugate, and then I'm going to put Br there. Now I know that that looks kind of weird, but that would be a technically correct formula, and I honestly think it'd be a little bit more technically correct than putting the H here. Okay, now my net ionic equation is going to be C5H5N plus H plus. So the strong acid, I'm going to leave out this little anion here. It's out, and then it is going to get together, and it's going to make C5H5NH plus. Okay, so this is always what you see when you have a weak base with a strong acid. The strong is just that kind of H flying out there. Alrighty, and this last one here is CH3, CH2, COOH, and that's NaOH here. So I maybe don't know what this is right away because it does have an OH in the formula, so that might throw me. But I do know that NaOH is a strong base. So that means that this guy here must be a weak acid because it's not one of the 6 or 7 strong acids, so it must be a weak acid if it's a neutralization reaction. This is actually propanoic acid. We use it in a different video if you've been keeping track. Okay, so if we think about what's going to happen here, this formula here is a little kind of gnarly to use, but if we remember, this COOH here is that carboxylic acid that they talk about. And if you remember the structure, it's that. So it's the double bonded carbon with the O connected to the H. This is the H it's going to leave. So what I like to do is I like to take this H off for the neutralization and add it together with the OH here. So we're going to make H2O. Okay. So this one H is going to come off. This one OH is going to come off here. And then it is going to leave me with this Na plus here. And then this whole thing, because I'm losing this H, is going to be a -1. So my salt is going to be NaCH3, CH2, COO. And it looks kind of goofy, but that's what's going to happen. So this is the propanoate, or I'm sorry, the propanoate ion, and then this is the sodium here. And so we've got that. So you ask yourself, what is the net ionic equation going to be? It is going to be CH3, CH2, COOH. So it's the whole formula for this weak acid because the weak acid doesn't ionize 100%, and it's going to get together with the OH minus, and it is going to make H2O and the propanoid ion CH3, CH2, COO minus. So in this case, the only thing that isn't included is the Na plus, that spectator ion there. So the strongs only contribute, they're either OH or H plus. The rest of them, though, they stay in the net ionic equations. We are going to do a ton more practice with this in class, but if you have any questions, please make sure you get them cleared up. Otherwise, good luck.